Very often, center of mass and momentum are taught together in physics. And the reason is that collisions can look really complicated when you have these big, gangly, messy objects colliding and spinning away from each other. Okay? But if you were to think of two objects as just points, it simplifies collisions. All right? It simplifies the motion of objects if you can just think of them as a point. And the best point to pick when you're trying to simplify an object is the center of mass. The center of mass is, as if you go to the slide that says center of mass, the most helpful approximation in all of physics. We can think of an object's mass to be concentrated in one point, okay? And that point is the center of mass. So every object has one of these. You, as a person, as a human being, have a center of mass, right? It's often thought of as the balancing point, right? So, for example, if I'm trying to balance this book of matches and I'm having a hard time, right? At some point, I'm going to find some point where it just balances, right? You get the idea. It's not perfect. Maybe this pencil will be better. Nope. Maybe here. Yeah. So the center of mass of this pencil is going to be right about there, which makes a little sense because you have this eraser and this metal here that's a little bit more dense than the wood, so it's going to be a little bit closer over there, okay? But human beings have one as well. Male bodies, the center of mass tends to be a little bit higher because male bodies often have, broad shoulders and these like kind of baboon, beefy, pecs, right? And then women's center of mass, or a female body, often is a little bit lower because hips are usually a little bit wider for females, right? Obviously, that's a generalization, but it's an interesting enough of a generalization that I'm sharing two videos where these men are unable, I should say boys, unable to perform these incredibly simple physical tasks because their center of mass won't allow them. It's actually pretty funny. So I recommend you guys check out those videos. But the bottom line is that all objects in the world have this quality of a center of mass, right? And you can look at it. So if you look at this picture on this center of mass slide here, you'll see this bat. That even though this bat is rotating, right, the center of mass of the bat follows the perfect little parabolic path. And that is, simply stated, why looking at center mass is so useful. Because no matter what other weird kind of motions an object is doing, the center of mass is going to act like the one part of an object that gravity is acting on the entire time, right? That has this perfect parabolic ballistic motion or projectile motion. So the question is, how do we actually calculate it? Okay, how do we actually find out where we could find the center of mass in an object? And this is especially important in engineering problems. So let's take a look at a situation where we have, let's say, a y and an x-axis, right? Let's say I have three objects in here. I have object 1, right? I have object 2, and I have object 3. Okay, and object 1 has mass 1, right? And it has a coordinate point x1, y1. Okay, so this guy has a mass of m1, and he's located at x1, y1. Okay, so that's x1, and that's y1, right? And then I have this second guy over here. He's got a mass of m2, and he's located at x2, y2. Okay, then I have this third point, mass 3, and it is located at x3, y3. All right, and so this configuration of masses is going to have a center of mass at some point, right? I don't know what it is, but I'll take a guess. I'll say it probably should be somewhere in between them, and it'll vary depending on how big these masses are, right? If M1 is much bigger than these guys, it'll be closer to M1, right? So let's say that right there is the center of mass, often abbreviated with CM, okay? So how can I find out what the center of mass will be for these three different objects? Okay, don't freak out, but these are the formulas. And they involve some sigmas, some sum signs, okay? But I promise you it's much easier than it looks, okay? So for this center of mass, let me remind you, will have a coordinate of x comma y, right? So the x coordinate of that center of mass is just going to be the sum of each mass times each x coordinate for each of these guys. So this x coordinate would be whatever the x coordinate is for 1, this x coordinate would be whatever the x coordinate is for 2, and this x coordinate would be whatever it is for 3 here, right? So it's the sum of all the mass times the x coordinates divided by the sum of all the masses, right? A lot of times you could just replace this as mi xi divided by the total mass of all these objects. Okay? And then the y center of mass, right, is just going to be the sum of, you guessed it, m's, the masses of each of these guys, times the y coordinate of each of these points over the sum of all the objects. And that also can be replaced by sum of mi, yi over the mass of all of them. Okay? Now, you may be like, whew, this is ugly. And you know what? It is the sort of thing where, if a little sibling or somebody who didn't take a lot of math in their lives looks at that and they'll be like, oh my God, this is some beautiful mind type stuff. This is some I use some kind of crazy genius. But it's actually not as complicated as it looks. And I will prove it by looking at the center of mass of a carbon molecule. Okay? So let's just take a simple carbon molecule. Here's our y-axis, here's our x-axis. Okay? And so we are going to say that, sorry, not a carbon monoxide molecule. Okay? And so I am going to say over here that this is our carbon, right? This is C, right? And this is going to be connected to an oxygen, which is a little bit bigger. Okay? And I want to find out what is the center of mass of this little molecule. Oh, sorry, oxygen. Oh. Okay? Carbon monoxide, right? So this is CO, carbon monoxide. And I want to find out where the center of mass is going to be, right? We want to find out between them what is this point that has the center of mass. Okay? And the glorious, and once again, that's going to have some coordinate, but this, if we make this nice and simple for us and say that this is all on the x-axis, right, then we can make this really simple for ourselves and just start here, right? This is all on the x-axis, so we don't have to deal with y. We just have to look at the center of mass in x. So let's explore it. The problem here on this slide that says the center of mass of carbon monoxide, it tells us that the mass of carbon, right, is 12 atomic mass units, and the mass of oxygen is 16 atomic mass units, right? And it also tells us the length of this bond. So this is x equals 0, obviously, right? And the length of the bond is 1.13 times 10 to the minus 10 meters, or 1.13 angstroms, okay? Using this information, we can find out what the center of mass is. What does that mean? That means that if I take a carbon monoxide molecule and I flip it and throw it, that we could replace the entire molecule with that point, thereby really, really simplifying the motion and the analysis of this molecule. Okay. All right. So we start with our equation. We say x, center of mass, is equal to the sum of each individual mass times each individual position divided by the sum of the masses total. Right? Okay. Well, what is our, so, and this is obviously a sum from I to n, right? For however many particles we have. These are all I to n. Now, what is our n? How many particles do we have? It's just 2. It's super easy, right? Let's start with carbon. Carbon has a mass of 12U, right? That's our M1, our M of carbon. times the position of carbon. It's at x equals 0, right? On the x-axis. So that's just 0. That makes our life really easy because then that just goes away. So it's a sum, so that's plus now the m and the x for the next particle, which is just oxygen. Okay? So we know that oxygen has a mass of 16 mass units, and its location is 1.13 times 10 to the minus 10 meters down the x-axis. So that is going to be 1.13 times 10 to the minus 10. Okay? And that's divided by the sum of each mass. So what is just the mass of carbon? 12U. What is just the mass of oxygen? 16U. Okay? So then I can just replace this with the center of mass of this carbon monoxide molecule is, well, this goes away. So that's just going to be 16U times 1.13 times 10 to the minus 10 divided by 12U plus 16U. Oh my God. Geez, what is that? It's going to be something like 28, right? 28U. Look at these little u's. These atomic mass units just cancel out. That's really convenient. So then if I just take 16 times 1.13 times 10 to the minus 10 divided by 28, I get a value of 6.5 times 10 to the minus 11. Okay? And that's meters. Yes. Okay. So this is 6.5. This means that 6.5 times 10 to the minus 11, that's about halfway, a little bit more than halfway to 1.13 times 10 to the minus 10. So actually, we're a little bit off here. It'll be a little bit closer to the oxygen. Does that make sense? Yeah, it totally makes sense. Oxygen is more massive. So we would expect the center of mass of this whole molecule to be a little bit closer to the heavier thing. All right? So these kind of crazy, beautiful mind-looking equations are really just simple things. We take the mass and the position of this, put it there. Take the mass and the position of this, add it. Right? If there was another molecule, we would do the same thing. Add that mass and position. Okay? And then divide by the total mass of everything. In this case, the atomic mass units will cancel, and we have an answer. We found the center of mass of carbon monoxide. And forevermore, if you are a biophysicist or a biochemist or a physical chemist that is analyzing carbon monoxide, you can, in a sense, replace this entire molecule with that one glorious point called the center of mass and make your life way easier for yourself. All right? In the next example, we're going to look at the case where it's not so simple and we don't just have one dimension, that we will actually have to take into account both x and y coordinates of the center of mass. I'll see you there.